Assalamu alaikum and good day everyone. How are you class? Hope fine. Today is our lecture number 4, unit electrostatics. Today's topics are electric field intensity, electric field due to a point charge, and I'm your teacher Muhammad Ikram. So I welcome you all into my class and let us begin. And one thing I would like to tell you that they seems to be very simple, but these are the very basic and the backbone of the entire second year course. Once you understand the concept here, inshallah, you don't feel any difficulty further. Most importantly, the electric field intensity in the electric field due to a point charge. The electric field and the electric field intensity you know from your previous class, but though I will explain it to you here in further detail. So let us start with the name of Allah Almighty. Bismillahir Rahmanir Rahim. Now, our first topic is the electric field. That what is the electric field? To be very simple, I would like to tell you that electric field is in fact it is the the area around, not the even, that is the, I would like to be very simple about it, that the area, to be very simple, we can say that the area where the electrostatic force, the electrostatic force acts is called the electric field, is called the electric field. Or simply you may say that it is the area or the region around charged particle where the electrostatic force acts, or where the electrostatic force can be experienced, is called the electric field. Electric field is, in fact, this is a vector quantity, a physical quantity which we sometimes consider as the vector quantity. It has a direction. Now let us see right over here that why we need the electric field. Because that, if you remember, I told you that electric field is in fact the electric field is in fact, electric charge is in fact the natural or the intrinsic property of a charged particle, which causes the electrostatic force of attraction or repulsion, depends of the type of the charge. But for every charged particle, whether electron, whether proton, or whether a charged body, electron or proton is not necessary only. So then there will be what? There will be the electric field associated with it. Since the electric field is not directly visible, then for this purpose, to represent the electric field, we use the concept of the electric lines of force. What? The concept of what? The concept of electric lines of force. Do not try to say forces. Electric lines of force. This. Why? because that what is actually the reason of saying it so. Since, as I told you, that electric fields specify the region or the space around charged particle where the electrostatic force can act. So for this purpose, because you know that this force is not visible directly, we can only see the effect. Therefore, we need to more to make it more clearer, we use the concept of the electric lines of force. Rather, you can say that this is one of the geometric representation of that electric force caused by charge, right? So that is why we need this concept. So when we need the electric lines of force concept. The second, I want to tell you another important points here before going further, and that is about, as I already told you about the point charge, right? Now today I just want to tell you another thing, that is the source charge and the test charge also, as I'll be using these terms down the road, and the test charge also. Now these are another terms I would like to, but before going into the electric lines of force, I would like to explain these terms to you. The point charge I already explained in my very first lecture in the that is introduction to the electrostatics. The source charge I would like to explain, and the test charge I also would like to explain. Now, what is the source charge? The source charge is the main charge, or which is the cause of the electric field. That is the main cause of what? The main cause of the electric field Sometime this can also be refer as the point charge itself also. So that is the main cause. Now the test charge is also a charge. It is not alu ka chalu. It is also a charge. So but what kind of charge is it? The test charge is, that is very minimal or small in quantity. Small in what? In quantity. So that it cannot disrupt the main, that is the electric field of the point charge. The electric field of the point or of the source charge. Source charge. This charge is usually, we always usually take the test charge. It is not necessary, we can take negative also, but mostly we consider it a positive charge usually, right? Because I told you that repulsion is the sure test. See, one, that will be a positive charge. So small quantity, it will be in small quantity. That cannot disrupt the electric field of the source charge. So what the hell is it there for? The test charge is only used to, that is to find, we use it to find the boundaries of the main electric field caused by the source charge. So this is only used for the purpose of what? For the purpose of detection. Because if you have a single isolated charge, for example, if we call this a single isolated charge, then from a single charge we cannot specify the electric field of a single charge. This is why a test charge is needed. So that is the difference between the test charge, the source charge, point charge are actually also the main cause, the main source of the charge or point charge. A charge is said to be a point charge that the two charges are said to be point charges if they have the distance between them smaller than the dimension of the charge. So we usually call that a point charge, right? So I will use the term source charge. I will use the term the test charge. So when I use these, you may understand them, that what the sir actually mean. Now let us come back to the electric field concept. So as I told you that the electric field is the space or region around the charged particle where the electrostatic force of attraction or repulsion acts is called the electric field. Now let us see, the electric field can be described geometrically by electric lines of force. Now, what are the electric lines of force? Let me tell you that the electric lines of force, what are the electric lines of force? Electric lines of force. Electric lines of force, these are in fact what? These are the imaginary lines because we cannot see. These are the imaginary lines which can be drawn around the charge or the charge particle. These are the imaginary line which can represent the electric field around a charged particle or of a charged body. Charged body in space. These are the imaginary line because we cannot see. So as you see it here, for example, that look here, I want to do it like here. For example, that is the diagram went up. So let me try it again. Rather, I don't like to use this. Okay, this is suppose, for example, a positive charge particle. So the electric lines of force are the field lines. How we can draw? First, that is, these lines are drawn radially outward for the positive charge. Radially outward for the positive charge. For what? For the positive charge. Radially outward for what? Radially outward for the positive charge. What does the radially outward means? Radially outward means making an angle of 90-degree with the surface of the charged particle, like this. And you just remember, you have to put the arrow in the middle somewhere, not there, because it will be then become a physical quantity of it, like force or like that. So this is why, to differentiate the electric field lines from that physical, any physical quantity, we just put the arrow in the middle. Second, like this one here, this one here, this one here, this one here, this one, this one, this one, and this one. So all the kind of think of, they are what? Electric field lines. electric field lines, right? Which indicates the electric field around any charged particle. Is it clear? Now let us see that. Look, I just want to draw another line and I'll be asking you that is it the electric field line like this line? It does not qualify the definition of not, an electric field line. Why? Because it does not qualify the definition. And what is the right definition for the qualifying like that? It is radially outward, drawn radially outward, making an angle of 90 degree with the surface. So this is not right. Now look, I will be revisiting this thing. For that is for the negative charge radially inward. For the negative charge, this is for the positive. So radially inward, these lines are drawn radially inward for the negative charge, So if you want to indicate the field for the negatively charged particle, these lines for the negatively charged particle, these lines will be drawn, what? They will be drawn radially again, but what? But this time inward, as you see. So these are the lines, right, as they are drawn radially inward for the negative charge. So it indicates the electric field. So this is field line, this is the field line, but if I want to draw, so if I ask you that whether this is a field, oh sorry, this is a field line, this is a field line, but if I want to draw this one, is this a field line? No, yeah, not. This is not a field line. Why? Because that it is not radially drawn. Radially means making 90 degree from the surface. Now the question is why? And that is one of the important reason for the radially outward or inward is that no, for an isolated charge, for a single charge. This is important. People sometimes ignore this thing. For a single charge, for a single charge, or for an isolated charge, because charge can coexist separately. For a single or isolated charge, no electric, no, for a single isolated charge, no two electric field lines can cross each other. This is impossible. Look, they will never cross each other. They will never cross each other for an isolated system of charges. If they were to cross each other, then there will be two electric field intensities at one point, which is physically not correct or not possible. And I will prove this thing to you, inshallah, when I teach you the electric field intensity. So this is what you must learn, that this is one of the reasons that they are drawn radially outward or inward for single charges, so that they may not cross because of uh, these things, because of the this condition. The second important point here is, but maybe the third one, that electric field lines where the electric field, or the electric, this could also be a point where that is the electric field is stronger, where the lines are closer, where what? Where the lines are closer. and weaker elsewhere, and weaker where the lines are spread apart are as if they diverge. So what does this means actually? This is one of the beautiful statement, and this statement signify what? That is, this statement actually refers to what? That this makes it the geometrical representation of the Coulomb's law, the inverse square law of the Coulomb. What? The inverse square law of the Coulomb. What does this means? That elect Coulomb force is inversely proportional to 1 over r square. So you see that, look, I just want to take you there somewhere in the upper part of the portion. You see here, look, see in the first case, look, here if you see in this diagram, the lines are what? In fact, the lines are closer in this region. You just see, look, the fields, that is, the field is what? The, the field, let me play this. As you see, look, media cannot be played. Okay. You just see, look, the field, you see that is, it is extended outward. Like this is the field due to what? Due to the electric field due to the positive charge. Now you see within this region, here you see the lines are closer. The lines are what? Lines closer. Lines closer. So the effect of the field is stronger within this region. And here, if you see, spread apart. Spread apart. So in this region, the field is weaker, right? So now look, this is one of the most important point. Here, second important point here, look at the fields of the, that was for an isolated charge. The lines are what? They do not cross each other. They closer where the field is stronger, far apart where the field is weaker. They are drawn normally outward for the positive charge, inward for the negative charge. In fact, the electric field is a geometrical representation of the Coulomb law. No two electric field lines can cross each other. Why? If they were to cross, there will be two electric field intensities, one point, which is not possible, and I will be explaining this thing to you. For the system of charges, let us see here, you have the two system of charges. In the system of charges, look, what you are seeing here. If you remember my very first lecture, in my that very first lecture, I told you that the electrostatic force of attraction or repulsion arises, it is because when the two fields interact together. So you see here in this demo, look, the electric field lines, due to what? Due to the positive charge. You just see, look, this is from the positive charge. Now the same happens here also. Now when you see that the two electric field lines, you just see, look, they exert a force of repulsion on each other, as you see. So it will repel it in this way, and it will repel this in this way. If I label it charge q1 and if I label it charge q2, then definitely what I will be calling it, that it is the force that one exert on two, and I will be calling it the force that two exerts on one, as you see. And here, what happens, since the forces are along, if you see, look, the forces are along what? The forces are along along the line joining the center of the two charge particle. So there the two forces cancel out the effect of each other. if they are the same in magnitude, as you see here at the center I would talk, elsewhere they can. So now you see the line may cross each other. Why? Because it is not isolated system, it is the combination of charges. So here at the center, if you just look at the center, they do cross each other right here. And what is the net force there? The net electrostatic force is zero at the center, right? At the center of these two, the charges combination, right? So this is how the electric field lines are for the combination of charge. Similarly, for that was for two like charges, now for two unlike charges. And now what you see here, as I told you, that for the negative charge radially inward, for the positive charge really outward. So they start from the positive charge and they ends at the negative charge. And here there is no region where the field is zero, right? The field is not zero anywhere in this region. Is it clear? And you see that look, they all are, they both attract each other here. But here one thing I would like to tell you, that the direction of the electric field intensity or the electric field is different at different point. Here that is, it will be drawn by using a tangent line. Here the direction of the electric field is E. Why? Because we denote the electric field by E, or the electric field intensity. Here the direction is which one? Here the direction is this one. Here, what is the direction of the, that is, I would like by this one, since this is what I'm representing, the electric field intensity, a physical quantity which is measurable. Here, what is the direction? Here the direction is this one. So you see, for the system of charges, at one point the direction is not the same, it may be different, right? So this is what, this is for the system of charges here. And you just see, look, in this simulation I will show you how the two causes the force of attraction or repulsion. Why? As I told you, when the field of the two charge interacts, they either give rise to repulsion in the previous case and attraction in this case. You see, look, see here. I think the video is not going to play. Let me do it. See here. Now, a next important point. Here you just see, look, here you have 2 coulomb of charge. And here you have what? 1 coulomb of charge, for example, as you see. So here the magnitude of the charge is greater, and here the magnitude of the charge is less. So you see here how many lines you do have more than that one. You just see, look, for each 1 coulomb of charge, 1 2 3 4 5 6 lines drawn, right? So look, then here definitely it will be 1 2 3 4 5 6 7 8 9 10 11 12. 12. Why? Because for the 1 coulomb of charge we draw 6 lines. So for the 2 coulomb of charge we will draw what? We will draw 12 lines. So you just see, look at this thing here, it causes a kind of attraction, kind of what? A kind of attraction here. So this is how the electrostatic the electric field lines can be represented. Another important point which I want to tell you about the electric field or the electric field lines, that these, in the previous cases, all the electric field was variable in much of the cases, not sorry, in all the cases. Here you see, look, due to a point charge, due to electric dipole, two similar charges, and due to the two positively charged plate, here the electric field is constant, uniform electric field, uniform electric field. Now the field, the electric field will be uniform. It is the same everywhere. Starting from the point, if you choose point A, or point B, or point C, in this region, the electric field intensity, later on I'll be explaining this thing, it is the same everywhere. Why? Because the lines are equally spaced. Here the electric field intensity varies, right? Why? Because the electric field lines are not equally spaced. The field is variable. So this I will also be explaining to you inshallah a bit later. Now let us come to another important point, the electric field intensity. Electric field intensity. The electric field intensity. Now, what is the electric field intensity? We can define the electric field intensity as a it is a kind of physical quantity which we can define as the that is the electrostatic force acting per unit charge place at that point. What? The electrostatic force acting per unit positive charge or per unit charge at at that point at that point. So electric field intensity, mathematically we can write the electric field intensity as the electrostatic force acting per unit test charge due to a source charge, right? This is equation number 1. The SI unit is what? The SI unit is Newton per coulomb, right? Physically, it is a vector quantity. It is what? Vector quantity. It is a vector quantity. Electric field intensity is said to be 1 Newton per coulomb. That is F 1 Newton of force. If a source charge exert 1 Newton of if a source charge exerts 1 Newton of force on a charge of 1 coulomb at that point, then it is called what? Then it is called the electric field intensity of 1 Newton per coulomb. The electric field intensity can also be measured in other quantities also. That is volt per meter. Later on, I will be explaining this thing to you, and this might be one of the question that they will ask you. Show that Newton per coulomb is equal to volt per meter. So later on I will be explaining this to you. So let us see that how is it like. For example, if we have if we have a charge, positive charge, with its electric field lines like this is drawn radially outward. This is what? Then what will be the electric field intensity at a particular point, right? Then, for example, this is the source charge Q, right? If we have a test charge, for example, let's say we have another test charge Q naught here. For example, if we have this at a point A, if this is what? That is another charge Q naught. We call this charge as a test charge. Then what will be the electric field intensity? Then the electric field intensity at that point will be what? The electric field intensity demonstrated is at that point like this, electric field intensity, the electrostatic force per unit charge at that point, at this point, the point A. That will be the electric field intensity. Why? Because you have one discharge and you have one discharge. So definitely there will be electrostatic force between the two. Now the question is that why we just do this thing? Look, as I told you that it is very difficult to apply the Coulomb's law because of its vector nature to various complex situations. So electric field intensity help us in calculating the electrostatic force at a particular point where the electric field intensity is known. So with by knowing the electric field intensity, we can calculate the Coulomb force at that point. So this is why it is very important. And I will explain this thing to you. The electric field intensity due to what? Electric field intensity due to a point charge, due to a point charge. And you will see it now, the same thing in this point. How did it help us? Like this one, for example, that look, if we have two charges, a source charge, this is what the source charge is, a source charge, and that is what we have, a test charge. So if you see, we have a source charge and we have what? And we have a test charge. Now, what is the electric field intensity there? The electric field intensity at the point A is electric field intensity. Electric field intensity at the point A. At the point A will be what? Due to that is, for that test charge, it will be what? The electric field intensity. It will be Fe by what? Q naught. This is equation number 1. And as I already told you that electric field intensity is what? It is a vector quantity, and its direction can be found by drawing a tangent line at that point. So since it is a single isolated charge, so it will be in the same direction as the direction of the electric field line. But for the combination of the charges, I explained it to you earlier when I was explaining to you the electric field lines, right? So you must keep that thing in your mind, that it is a vector quantity and its direction can be found by drawing a tangent line at that point. Now, now let us see that since if you just look here, that is the for the two charges, as you see, look, these two charges, they are how much distance apart? If you see, they are r distance apart. The distance between their center is what? R and R. So the by the definition of the electric field intensity, we have won this equation, right? And so I can find an equation for the electric field intensity as Q naught into E. So what does this means? That the electrostatic force between the two charged particles is equal to what? It is equal to Q naught times into the electric field intensity at that point. But from the Coulomb's law, but from what? From the Coulomb's law, from the Coulomb's law, what we can write? That the electric field, that is, that the electrostatic force is equal to what? K, Q1, so here we have Q, the source charge, Q2, which we have a test charge, divided like by R square. So compare, this is 3. Comparing what? Comparing 2 and 3. What we can then write if we compare the two equations? So we can write that Q naught E is equal K Q naught by R square. So what does this mean? That electric field intensity is equal, this Q naught and Q naught get cancelled, and you have the K Q by R square. So now what does this mean? That E is equal to what? K is equal to 1 over 4 pi into epsilon naught for into what? Into Q by R square. This is one of the most important equation. The equation is not important by itself. The result of the equation, let us see. What is the result? The result is that E is directly proportional to Q. E is inversely proportional to 1 over R square. Inverse square law. Here, this is why we are always interested in what? Or always interested in what? Interested in the magnitude of the source charge. The magnitude of what? Of the source charge. We are interested in what? We are interested in the magnitude of the source charge. That greater the magnitude of the source charge, greater will be the electric field intensity. This is one result. This is the second result, right? And second, that the field, electric field intensity varies, decreases by 1 over r square. And the third important point is medium dependent. That E depends on what? Depends on the nature of the medium. The nature of the medium. So the electric field intensity at a point depends on the magnitude of the source charge, not of the test charge. Remember, that is very important. And it depends on the inverse square law. What does this mean? For example, this is so important that, for example, if we have a charge, let us see like this, right? If we have here a charge, Q source charge, so we can find the electric field intensity anywhere at any of the point without knowing the magnitude of the test charge. You can find the electric field intensity at the point A, at the point B, at the point C, at the point D, at the point E, anywhere. Like we can find electric field intensity anywhere without knowing the magnitude of the test charge. F, that is, what does this means? That is F, the magnitude of the source charge. If the magnitude of the source charge is known, we can find what? We can find the electric field intensity. Electric field intensity anywhere in the region. Anywhere in the region, right? So this is one. If the distance is known, right? That is what? At any distance, at any known distance. So we do not need a second charge, right? But this is, what does this result? Another result important, that by knowing the electric field intensity, by knowing the electric field intensity, we can calculate the Coulomb force, yeah, the electrostatic force of what? The electrostatic force of attraction or repulsion, for any charge tester like that. Why? Because we can write that electrostatic force is equal to what? Q naught into E, right? So if you know the electric field intensity of the source charge, you can simply do it for any combination of the charge, any test charge quantity. You can calculate the electrostatic force. So this is what? A bit easier approach than using the Coulomb law directly. So that is our today lecture. Hope you understand much of our from today lecture. So thank you very much. And if you have any question, you can ask. I will give assignment on the WhatsApp initially.